Hello everyone, my name is Samita Garg and I'm going to teach you control system. In the control system, today's topic is transfer function and block diagram reduction technique, which is very important topic. Now the first is, what is the transfer function? Transfer function is what? What is the use of this transfer function? A transfer function is a convenient way to represent a linear time invariant system in terms of its input-output relationship. The key advantage of the transfer function is that they allow engineers to use simple algebraic equations instead of complex differential equations for analyzing the designing systems. Now, in the transfer function, we use always gain. The frequency response or gain of the system is defined as the absolute value of the ratio of the output, amplitude of the steady state input amplitude, which is just the absolute value of the transfer function. So that the transfer function is defined as, this is the ratio of Laplace transform of the output to the Laplace transform of the input of the system. We are considering all initial conditions to be 0. Now here we take all initial conditions are 0. If your system has non-zero initial conditions, we will have to do some extra work, and because of this transfer function all the initial conditions are 0, we can simplify the system in more convenient way. Now, here this is the input of the system, plant, that is process, and this is the output of the system. If we have taken the Laplace transform of this input, we get here US. And here this is the Laplace transform of YT. This is equal to what? YS. Where L is what? This is called the Laplace operator. So to find out the transfer function, first take the Laplace transform of the differential equation with 0 initial conditions. Recall the differentiation in the time domain is equivalent to multiplied by operator S. In the Laplace domain, the transfer function is then the ratio of the output to the input, is called transfer function. The transfer function of the plant is given as this GS is equal to output of Laplace transform of output upon Laplace transform of input when all initial conditions are taken as 0. So that this is US given to the plant or process or the system whose transfer function is GS, and this is the output YS. Now, why we take this initial conditions are 0? One of the assumptions for the construction of the transfer function, we have taken all initial conditions of 0. The input response, initial condition, we have to find all the dynamic equations for the transfer function and set the input at 0. So that we always ignore this initial conditions, because in initial conditions there will be not much value which will affect on the system. By the use of the Laplace transform, we can convert many common functions into algebraic function of complex variable x. For example, if this is the Laplace transform of sine omega t, we will have this Laplace transform of sine omega t is equals to omega upon s square plus omega square. And Laplace transform of e raised to power minus at, this will be equal to 1 by s plus e, where s is a complex variable or complex frequency and is given as S is equal to sigma plus G, where sigma is the real part of the system and this J shows the imaginary part of the system. Consider the following differential equation where yt is the input of the system and xt is the output of the system. Here, this is the differential equation. A d2xt upon dt square is equals to c dyt upon dt minus dxt upon dt. Suppose this is a ordinary differential equation. Here, this can be written like this. Taking the Laplace transform of on the both the sides, we get a, because this is double differential operation, this can be represented by s square xs minus s x0 minus x dash 0. This will be equal to c s ys minus y0 and so on this. Here x0, y0, x dash 0, this all represents the initial condition so that we can ignore them or we will put their values equal to 0. Now considering initial conditions to 0 in order to find the transfer function of the system. A s square xs minus is equals to c s ys minus b s xs. Okay. When we put all the initial conditions are equal to 0, we get this equation. On rearranging this above equation, what we get? A s square xs is equals to bs is taken in the left hand side is equals to this. So that xs output is taken on the either side and ys is taken on the other side. So that this will be xs upon ys is equal to this and we get this transfer function c upon as plus b. Now in general, this differential equation can be of any nth or mth order equation. This can be represented as a naught raised to power ny plus a1 raised to power n minus 1 plus and so on an minus 1 y dot. So it represents the differential value of y and this is a and y is equals to b naught raised to power m x plus b1 raised to power m minus 1 x plus and so on bn minus 1 x dot plus bn x, where x is the input of the system and y is the output of the system. On the transfer function we get transfer function is equal to Laplace transform of output upon Laplace transform of input. When all initial conditions are equal to 0, we get ys upon xs is equals to like this. Where order of the denominator polynomial is greater than the numerator polynomial, the transfer function is said to be proper. Otherwise, this is called improper. When the order of the denominator polynomial equation is greater than the numerator polynomial equation, this is called the proper equation. Now first, this is shown here electrical system in which we have to find out the transfer function. Here we use resistance R and the inductance L, and here this is the voltage is used as the input signal and this current I is taken as the output signal. From the circuit we get an equation because here this is a common current which is flowing in this whole circuit. There V is equals to, by using the KVL law, we get R into IT plus LdIt by dt. Now applying the Laplace transform on this expression, what we get? Laplace transform of V is equal to Vs is equal to R into Is plus L. Laplace transform of this differential is S into Is. So that if we get Is upon output upon input, Laplace transform of output upon Laplace transform of input is equal to 1 upon R plus Ls is equal to 1 by L upon R S plus R by L. We have taken this equation into S plus A, S plus B form. The transfer function of the system Gs is equal to Is upon Bs, the ratio of the output to the input. Now second example, here we have taken R. This is the capacitance C. Here we take one input signal, voltage signal, input signal, E input, and the other voltage is taken as a output. In the above network, it is obvious that let us assume current I is flowing, that is common in this circuit, so that E input will be equal to what? The current is flowing in this resistance R, that is RIT, and the current I is flowing in this capacitance. This is 1 upon C integral of IT dt, and this output voltage is equal to this terminal voltage. So there is no element, so that this output voltage is equal to the voltage of this terminal. So that the voltage of this terminal is what? This is 1 by C integral of IT into dt. On taking the Laplace transform of both these two equations, what we get? E inputs is equal to RIS plus integral of 1 by C IS upon S is equals to IS this, and E output is equals to this integral of IT into dt. This will be equal to the Laplace transform of integral function is IS upon S is equal to IS upon CS. Transfer function of the network E output upon E input is equals to this, and we can get like this. This is the transfer function. So that in this process, by this process, we can find out the transfer function of any system or of any element, because every element has their own input and we get the output. Now the block diagram reduction. This block diagram reduction technique is very important. If we have a complex system, we can convert this into a simple function by this block diagram reduction technique, and so that we can find out the overall transfer function of the system. A block diagram is basically modeling of any simple or complex system. It consists of multiple blocks connected together to represent a symbol to explain how it is functioning. In the simplified form, we get always this is the reference input, this is the transfer function of overall system, and we get the controlled output. So that transfer function of the system is equals to output Laplace transform of output upon Laplace transform of input, considering all initial conditions are 0. And this is the complex function, and we have simplified this into this form by using this technique. Here G1, G2, G3, G4, these all represents the transfer function of the elements which are connected in the forward path. So that G1, this is the transfer function of one element, G2, this is the transfer function of the other element, and so on, and these are connected in forward path. So that G1, G2, G3, G4, these all are known as forward path transfer functions. Here H1, H2, these are the elements which are connected in feedback. So that they are known as the feedback transfer function. It is normally need of the block diagram reduction. It is normally required to reduce multiple blocks into a single block, or for convenient understanding, it may sometimes require to rearrange the blocks from its original order. For the calculation of transfer function, it's required to be reduced. Now, what are the techniques to reduce the block diagram into the simplified diagram? We have to remember all these techniques. Combining blocks which are connected in cascade or in parallel. Now, G1, G2, here when the input of the other system is work as a input for the other system, that is known as the cascade. This is the G1 and this is the G2. Both are connected in cascade. There is no element in between them, so that this will be equal to what? G1, G2. We will multiply both these two transfer functions and we can convert this into a simplified form. And here G1 and G2 both are connected in parallel through this adder or this summing point. So that G1 and G2, both these will be adding, we get G1 plus G2. Now moving a summing point behind a block to after a block. if we move this summing point from behind the block to after the block, what we get when we this jump from behind the block to this after the block, there will be addition of one more block which is equal to the same transfer function. This is G, this is again G. Now what will happen when this uh, summing point is moving from after to before this block? This will be the inverse function, so that when this summing point will move from after to before this block, we will get inverse of this transfer function. So that this will be equal to what? 1 by G. Now moving a pickoff point behind a block. This is called a pickup point, where the other, this is the junction where we can add other block. So that this is called the pickup point. When this move from behind the block to after the block, this will be the inverse of the function we have here. This is 1 by G. We add one more block which is inverse of this transfer function. And if the picker point is moving from after the block to before the block, this will be same as G. We add one other block which will be equal to same that transfer function G. Moving a summing point ahead of the block, if we move this summing point after the block to before the block, this will be equal to this. Moving a point out. Yeah, we have already discussed this. Now, eliminating a feedback loop. If we eliminate this feedback loop to simplify this block diagram in a simple form in a single block, then we get this type of expression. In the next slide, we will discuss how we'll get this type of the simplified block diagram. But you have to remember this result also. This is G upon 1 minus plus GH. This minus plus depends on the feedback. If this is positive feedback, we put here minus. If this is negative feedback, minus, we put it here plus. And if this feedback is equal to 1, this is called unity feedback system. So that this will be equal to G upon 1 minus plus G. In place of H, we put it here 1. Now swapping of two adjacent summing points, we can swap these two adjacent summing points and there will be no effect on the output. A and B can be interchanged. So these all are the techniques for the block diagram reduction. In the next slide, we will take few examples. Okay, thank you so much.